In the marble roller coaster lab, you guys released a marble from up here and you used a photo gate to time how fast it was actually moving at a whole bunch of different points along this thing's path. You also measured the height at different points in its path, and from that you were able to plot potential energy, kinetic energy, and add those two things up to come up with mechanical energy. Now, the potential energy graph probably didn't surprise you at all. The potential energy graph should have just looked exactly like this roller coaster, right? The higher it is, the more potential energy it has, because all we have is mgh, mass times gravity times height. The mass never changed, g never changes, but the height did. So when it's high, it had lots of energy. When it was low, it had a little potential energy. Now, the kinetic energy graph, so I guess I'll go ahead and draw this real quick. Our potential energy graph looked essentially like the roller coaster track. So potential energy versus position. So this is the potential energy of the marble versus its horizontal position as it moved across this track. And it started high, went low, came high, went low, and stayed there. Okay, and it just followed the height of the track. Now the kinetic energy was equal to 1/2 mv squared. Again, mass never changed, half is a constant. The velocity did. Right here, where it was right at the top, it had basically zero kinetic energy because we released it from rest. Now, at the bottom of the first hill, it's going to have the highest amount of kinetic energy because the entire time it's coming down that hill, it's speeding up, then it slows back down, and then it speeds back up. And so we end up with our kinetic energy graph that looks essentially like this. Now, if the law of conservation of energy does what we know it does, and that is to say that the total energy isn't changing except unless friction acts, then when we add those two things up, when we add our kinetic energy versus our potential energy, we should get a mechanical energy, and we would expect one or two things. We'd either expect that this line stays perfectly horizontal right here, mechanical energy, or maybe that it comes down a little bit in time, and this would be mechanical energy plus the work done by friction. And since friction is going to reduce the amount of energy, we would expect this to go down over time a little bit. But when you actually add those two lines up together, you don't get that. You get a line that looks more or less like the potential energy line, but shifted up. Okay, it's not as pronounced, and it's got less deep and high crests and valleys, but it does still go through the crest and valley thing, and that presents an issue with us, because if it was just friction doing that work, then that energy should just go down, and it's clearly got to be something more than that. Well, you got to think about the motion of the marble. It's doing more than just moving, okay? And what I mean by that is, if you have a car and you release it from rest, it moves along this path. And we think of this as translationally moving. It's basically sliding along this path. But, and really I shouldn't even have wheels on it. I should just have like a little block. If I release the block or sled, it slides along the path. But we didn't use a block. We used a marble. And when we use a marble and we let it roll, then instead of it just sliding along the path, it actually rolls along the path. And that means down here at the bottom of this hill, it's not only moving fast this way, it's also spinning fast this way. And that motion, that spinning motion, actually is required a little bit of kinetic energy to get that to happen. It's got some kinetic energy simply due to its rotation. I want you to think about a disc or a pulley. It's just sitting here. It's not spinning, it's not doing anything. If you're going to make it spin, then you have to apply a force through a distance to get this thing to spin. And that work is not gone. You did that work and it increased the rotational kinetic energy of this disc. It made it spin faster. Same thing happens with this marble as it comes down the track. Some of the energy right here at the top, we think of it as all being potential energy, and down here at the bottom we think of it as all being kinetic energy. But there's also some rotational energy that we didn't account for. Now, that energy, it is not accounted for in anything, because our potential energy we're accounting for with our height. Kinetic energy we're accounting for with our velocity, but our rotational energy, we didn't account for that anywhere. We didn't put it into any of our calculations. And then when this thing comes back up over here, it's going really, really slow again, which means it's not spinning very fast either. So up here we essentially have potential energy again, not very much kinetic energy, not very much rotational energy, which is why our mechanical energy line goes down and comes back up. If we actually could figure out how much rotational energy the ball had, we would see at the low spots it has a little bit more rotational energy, at the high spots it has a little bit less, and we're going to get a straight mechanical energy line, just like we think should happen. The problem is we did not account for all of the energy.